So chances are you've used something like ChatGPT to write an email, maybe summarize a long article. We've all seen these large language models in action. They become common, almost everyday tools. But the technology that's powering them, it's evolving into something way, way bigger. We're moving from tools that just respond to us to systems that can actually act on their own. Okay, let's get into it.
Right? We interact with these things constantly. We ask them to write for us, to code for us, to create. But have you ever really stopped and wondered what's going on under the hood? How in the world does a machine go from a simple line of text to a complex, coherent answer? Well, in this explainer, we're going to peel back those layers, moving from just being a user to thinking like an architect.
To really understand where AI is going, you gotta start with where it all begins. And the foundation for basically everything we're seeing today is the large language model, or what everyone calls an LLM. It's a fascinating system that turns a really simple idea, prediction, into what feels like a powerful conversation. So, what is an LLM at its very core? Honestly, it's a super sophisticated prediction machine. It's been trained on a massive, almost unimaginable chunk of the internet: books, articles, websites, you name it. And its fundamental job is surprisingly simple. It just predicts the next word in a sequence. That's it. And believe it or not, that one powerful idea is the key to everything else it can do.
Now, how does a computer see our language? Well, it doesn't read words like you and I do. First, our text gets chopped up into these smaller pieces called tokens. Then, each of those tokens is converted into a long list of numbers. That's the embedding, which captures its meaning. From that point on, it's all just math. The model is just crunching numbers to predict the next set of numbers, which then becomes the next token.
The real magic, the thing that allows an LLM to understand not just words, but context, comes from a very specific design called the transformer architecture. This is the engine that powers all modern AI, and it's what gives these models their almost spooky ability to reason. Let's look closer at tokenization. As the slide shows, it's all about breaking words into their basic parts. So a word like unhappily isn't just one thing. The model sees its components: the prefix un, the root happy, and the suffix ly. This is so clever because it lets the model understand grammar and even figure out the meaning of complex words it's never officially seen before.
So once we have tokens, they become embeddings. And you can think of embeddings as coordinates in a giant multi-dimensional map of meaning. Words with similar meanings, like car and automobile, are basically neighbors on this map. It's so powerful, you can literally do math with words. The famous example is if you take the vector for king, subtract man, and add woman, you land right next to the vector for queen. It's just wild.
Now, this slide points to the absolute breakthrough of the transformer, something called the self-attention mechanism. Instead of reading a sentence one word at a time from left to right, it looks at every single word at the exact same time, and it figures out which other words in the sentence are most important for understanding the full context of any given word. This is how it gets the nuance, the subtlety of human language. Okay, this is a really crucial point to understand. An AI model really has two totally different lives: the time it spends learning and the time it spends doing. We call these training and inference. They are completely different processes with very different goals. Training is the slow, incredibly expensive, and computationally massive process of teaching the model. It's like sending it to college. It involves thousands of GPUs running for weeks or months just to find patterns in data. Inference, on the other hand, is the doing part. It's fast, it's efficient, and it happens every single time you ask the AI a question. It's the model applying what it learned to give you an answer in real time. And when we say massive data sets, we are not exaggerating. I mean, look at this breakdown for a model like GPT-3. 60% of its knowledge comes from the Common Crawl, which is just a general scan of the public web. The rest is a mix of higher quality web text, millions of books, and the entirety of Wikipedia. That's the digital universe it learned from. I love this quote from Andrej Karpathy because it perfectly captures the shift in thinking here. We're moving away from what he calls software 1.0, where humans write explicit code, line by line. We're now in the era of software 2.0, where instead of writing code, we just show the computer tons of data and let an optimization process figure out the program for us. We're programming with data itself. Okay, so we've covered the basics of how an LLM works, but now we get to the really exciting part. We are living through the leap from passive models that just generate text to active, autonomous agents that can actually take action out in the world.
And this visual illustrates the difference so perfectly. A standard LLM is transactional. You give it an input, it thinks, it gives you an output. That's it. It waits for the next command. Agentic AI, though, is iterative. It gets a goal, it makes a plan, it takes an action, it observes the outcome, and then it corrects its own plan to try again. It's a continuous loop.
So how do you actually build one of these autonomous agents? Well, it's not just about having a powerful LLM. It's about building a whole cognitive architecture, a kind of scaffolding around that model to give it the ability to reason and act over and over again in that loop. Look at this diagram. The LLM is the reasoning kernel, right there at the center. You can think of it as the brain. But the agency, the ability to act on its own, that comes from the other components you build around it: the planning module, the memory system, and the tools it can use to interact with the world. So the first pillar is planning. An agent has to be able to take a big, vague goal from a human, like research solid-state batteries, and break it down into a concrete, logical plan. As you can see here, that might mean steps like searching for academic papers, summarizing them, and synthesizing the findings. This is so important because if the plan is flawed, the execution doesn't really matter. Next up is memory. You can't be an effective agent if you're forgetful. So agents have short-term memory to keep track of the current task, but more importantly, they have long-term memory. This is often a vector database where they can store past experiences and learnings to pull from later. This is what gives an agent persistence and lets it get smarter over time. Pillar 3 is where the rubber meets the road: tool use. This is how the agent actually connects its internal thinking to the outside world. It uses tools like APIs to do things: search the web, run some code, maybe even send an email. If the LLM is the brain, the tools are its hands. And finally, we have what might be the most important part of all: the feedback loop. The agent acts, it sees what happened, reflects on it, and then self-corrects for the next go-around. Now, this is a huge paradigm shift. In traditional software, an error is a failure. It crashes the program. In an agentic system, an error is just new information. It's just input for the next loop. So when you put all of these pieces together, you get a really profound shift. We're moving from just thinking about software as a tool that makes us more productive to thinking about it as a kind of digital labor, a system that you can give complex goals to and let it work autonomously to get them done. And this is maybe the most important takeaway from all of this. What we just walked through might feel like magic, like some kind of unknowable black box, but it's not. It is a system. A complex one, yes, but a system built with clear, understandable architectural principles. This is engineering. So as we wrap up, I want to leave you with this thought. The key skill of the future isn't just going to be about writing a good prompt for a chatbot. The future belongs to those who can design, build, and orchestrate these autonomous loops. That is where the true power of this technology is about to be unlocked.